Welcome to The Explainer. Today, we're breaking down a really fundamental tool in data science, logistic regression. It's all about moving from a simple if something happens to how likely it is to happen. It's the magic behind figuring out if a customer is going to click buy or not, or even predicting whether a patient might have a certain illness. It's all about those yes or no questions.
All right, here's what we've got on tap. First, we're going to dig into why we even need this thing in the first place. Then, we'll get into the fun part, interpreting those magic numbers the model spits out. After that, we'll ask the big question, is the model even any good? And what do we do when it gets a little overeager? And finally, we'll peek beyond the simple two-choice world.
All right, first up, predicting yes or no, when a straight line just won't cut it. So, yeah, why do we even need another type of regression? Don't we have linear regression for that? Okay, so take a look at this. On the left, you've got your trusty linear regression. It's fantastic for predicting a number, like the price of a house or the temperature tomorrow. But try to use that same logic for a simple yes or no choice, and it just falls apart. See that line on the right? It shoots off past 1 and way below 0. What does a probability of 150% even mean? Or negative 20%? It's just nonsense.
So that's the big problem, right? How do we build a model that knows its limits? One that only ever gives us an answer between 0 and 1. And the answer is just so elegant. It's this beautiful logistic S-curve. The genius of this thing is that it takes any number you throw at it, positive, negative, huge, tiny, whatever, and it squishes it into a value that's always, always between 0 and 1. And that, right there, is perfect for us. It's exactly what a probability looks like.
Okay, moving on to interpreting the magic numbers, how we decode the model's output. So we've got our S-curve, we've got our probability, but what are the numbers inside the model actually telling us? Let's jump into an example and see if we can crack the code.
So check this out. Imagine we built a model to predict whether a student will pass their final exam. And our model looks at two things, the student's gender and the number of practice exams they took. The model runs and spits out this table. These coefficient estimates are what we're really interested in right now. They're the core of the model's logic.
Okay, now here's the trick, and it's a big one. These coefficients, they're not probabilities. They're not even percentages. They're in this weird unit called log odds. It's kind of like the model is speaking a different language. It's mathematically convenient, but for us humans, it's not intuitive at all. So our job is to translate it. And here's how we translate it. We just take E, that mathematical constant, don't worry too much about it, and raise it to the power of our coefficient. So for practice exams, the coefficient was 1.13. We calculate e to the power of 1.13, and boom, we get 3.09. This new number is called an odds ratio, and this is something we can actually work with.
And what this means is actually pretty incredible. It means that for every single extra practice exam a student takes, their odds of passing get multiplied by 3.09. To put that another way, their odds go up by 209%. All of a sudden, that weird log odds number has turned into a really powerful, really clear insight.
And hey, this whole translation thing works for categories too. See the negative coefficient for being male? When we do the same math on that, it tells us that in this particular data set, being male was associated with 43% lower odds of passing the exam compared to females, assuming they took the same number of practice tests. All right, section 3, is your model any good? Because, moving beyond simple accuracy is key. We can interpret what the model is saying, which is great, but that doesn't mean what it's saying is right. So, how do we actually check its work?
Well, one of the most important tools we have is something called a confusion matrix. It sounds complicated, but it's really just a simple scorecard. It neatly organizes all the predictions into 4 buckets, where the model guessed yes and was right, where it guessed no and was right, and, most importantly, where it got things wrong. So this leads to a really common trap. Let's say you build a model and it's 95% accurate. That's an A+, right? It must be a fantastic model.
Well, not always. High accuracy can be super misleading, especially when you're dealing with something rare. Think about it. Imagine you're trying to predict a rare disease that only 1 out of 100 people has. A model could just be lazy and predict no disease for everyone. That model would be 99% accurate, but it would be completely, utterly useless because it would never find a single sick person. And that's exactly why we need other scores, like precision. Precision answers a very specific question. Of all the times the model cried wolf and said yes, How often was there actually a wolf? For our lazy disease model, a precision would be 0. It's super important in cases where being wrong about a yes is a big deal, like flagging a legitimate credit card purchase as fraud. It's all about the quality of your positive predictions. Okay, on to our next section, fixing an overeager model, or how to tame complexity with regularization. So we've got a model, we know how to measure it, but there's another, more subtle problem that can sneak in. And that problem is called overfitting. This is when the model gets too smart for its own good. It doesn't just learn the patterns in the data you show it, it starts to memorize the quirks and the noise. It's like a student who memorizes the answers for one specific test, but has no idea how to solve a new problem. It looks great in practice, but it fails in the real world. So how do we fix this? One of the best tools we have is called regularization. Think of it like a penalty system. We're telling the model, hey, you can learn from the data, but I'm going to penalize you for getting too confident about any one single thing. It basically forces the model to be a bit more skeptical and not latch on to every little detail, which helps it see the bigger picture. And you can literally see it in action here. This is a model that's looking at words to predict sentiment. With no penalty, words like love and disappointed have these huge coefficients. The model's really latching onto them. But watch what happens as we increase the penalty. All those coefficients get smaller and smaller, shrinking towards 0. We're basically taming the model, telling it to calm down and not be so extreme.
All right, final section, beyond 2 choices. So far, everything has been black and white, yes or no, pass or fail. But what happens when there are more than 2 options on the table?
Well, for that, we have something called multinomial logistic regression. It's basically the same idea we've been talking about, just leveled up for problems with 3, 4, or even dozens of possible outcomes. This is what you'd use to predict which major a student will choose, or which candidate a person will vote for, or even which blood type someone has. It's incredibly versatile.
Okay, so let's wrap this up with the key takeaways. First, logistic regression is all about predicting probabilities. That S-curve is key. Second, those weird coefficients aren't scary. We just have to translate them into odds ratios to understand them. Third, remember the accuracy trap. We have to look at other metrics, like precision, to know if a model is actually useful. And finally, regularization is our friend. It's the safety brake that stops our models from overfitting and failing when they see new data. And that brings us to a final, really important thought. These models are being used everywhere for really high-stakes decisions, things like loan applications, hiring, even medical diagnoses. So we know how to build them, and we know how to check if they're accurate. But the bigger question we all have to ask is, how do we make sure they're not just accurate, but also fair? How do we use this power responsibly?